The universe, with its immense scale and diversity of astronomical phenomena, constantly perplexes humanity. Among all the mysterious phenomena we've discovered, black holes are perhaps the most fascinating and least understood. Black holes not only challenge the laws of physics, but also compel us to ponder what lies beyond human comprehension. The question arises, what is a black hole? What do we know about black holes? And how can we study something that cannot be seen? The formation of black holes may offer key insights into the workings of the universe and the fundamental principles of physics, including gravity, time, and space. The journey to decode black holes goes beyond mere observation and sparks scientific revolutions in our understanding of the vast universe. A black hole is a region of space-time where the gravitational pull is so immense that nothing, not even light, can escape. This makes black holes invisible to us, as there is no light for the naked eye or astronomical instruments to detect. However, the existence of black holes is no longer just theoretical. It has been confirmed through various phenomena and astronomical observations. Black holes are formed from the collapse of a massive star after it exhausts the fuel in its core. When a supernova explosion occurs, the star's core is compressed by its own gravity to such an extent that nothing can resist this compression. As a result, the star collapses in on itself, forming a black hole with infinite density, where all concepts of time and space as we know them completely break down. The core of a black hole is called a singularity, a point where all matter collapses into a spot of infinite density and zero volume. Current theories suggest that the laws of physics as we know them cannot exist at this singularity, making it a region modern science cannot yet fully explain. Another crucial concept related to black holes is the event horizon, the boundary surrounding the singularity. Once anything, including light, crosses the event horizon, it can never return, and all information about it is lost to an outside observer. The event horizon is what gives black holes their name, as beyond this point, no signals or light can escape. This boundary is where space-time theories become enigmatic, challenging the fundamental laws of physics and creating mysteries that remain unsolved. According to Albert Einstein's theory of general relativity, gravity is not a force in the traditional sense, but rather the curvature of space-time caused by the presence of a massive object. Stars and planets create curved regions of space, and in the case of a black hole, this curvature is so extreme that nothing can escape from it. Both space and time are distorted around a black hole. As matter approaches the event horizon, time appears to slow down relative to distant observers, a phenomenon known as time dilation. This effect is a crucial aspect of Einstein's theory, demonstrating how black holes significantly alter our understanding of space-time. The concept of black holes is not a recent discovery. In 1783, British physicist John Michell introduced the idea of a dark star, an object with such strong gravity that light could not escape from it. This marked the first step towards the modern understanding of black holes. However, it wasn't until the early 20th century, with the development of Albert Einstein's theory of general relativity, that the black hole concept was correctly understood. In 1916, German physicist Karl Schwarzschild solved Einstein's equations to describe a non-rotating black hole, which became known as the Schwarzschild black hole. His groundbreaking work provided the first mathematical description of black holes, laying the foundation for further research into these mysterious objects. Black holes don't exist in just one form. They come in various types based on their size and formation process. Currently, scientists classify black holes into three main types. Stellar black holes. Stellar black holes are the most common type, formed from the collapse of massive stars after they run out of fuel. When a star with a mass over 10 times that of the sun exhausts its energy, it may collapse into a stellar black hole. These black holes have a mass ranging from 3 to 10 times that of the sun and are the remnants of supernova explosions. Supermassive black holes. Supermassive black holes are among the most important astronomical objects studied by scientists. With masses ranging from millions to billions of times that of the sun, they are typically found at the center of large galaxies, including our own Milky Way. A prime example is Sagittarius A star, the supermassive black hole at the center of the Milky Way, with a mass exceeding 4 million times that of the Sun. These black holes play a crucial role in shaping the dynamics of galaxies. Primordial black holes. Primordial black holes are a theoretical type believed to have formed shortly after the Big Bang, during the early moments of the universe. If small regions of the early universe had a higher than average density, they could have collapsed into black holes shortly after the universe began. Primordial black holes may be relatively small, and some theories suggest that they may have existed in various forms throughout the universe's history. Black holes serve as a perfect demonstration of Einstein's general theory of relativity. While Newton's theory of gravity described gravity as a force between two objects, Einstein's theory redefined gravity as the curvature of space-time caused by the presence of mass. Black holes don't just bend space, they warp time as well. This means that time inside a black hole flows differently compared to time outside. To a distant observer, an object falling into a black hole appears to slow down and eventually freeze at the event horizon. However, from the perspective of the object falling in, time flows normally. This is a classic example of time dilation, a phenomenon predicted by general relativity. One of the biggest challenges facing scientists today is the information paradox. According to classical physics, when an object falls into a black hole, all information about it is lost. But quantum mechanics states that information can never be destroyed. This creates a conflict between two of physics' major theories, general relativity and quantum mechanics, and has been a focus of efforts by scientists like Stephen Hawking to resolve. Black holes, especially supermassive black holes, play a crucial role in the evolution of galaxies. A black hole at the center of a galaxy is not just a passive hole, but can actively influence gravitational and energetic processes in its surrounding region. A prime example is the relativistic jets emitted by supermassive black holes, which can extend for hundreds of thousands of light years. These jets release vast amounts of energy and can affect star formation within the galaxy. In fact, some studies suggest that black holes may regulate the formation of new stars in a galaxy by either expelling or attracting clouds of gas and dust, which are essential materials for star creation. Additionally, black holes are key to explaining the phenomenon of redshift. When light from stars or galaxies near a black hole is stretched due to strong gravitational effects, its wavelength shifts towards the red end of the spectrum. This shift helps astronomers indirectly study black holes by observing the light from surrounding celestial objects. Although black holes cannot be observed directly, modern technologies allow us to study their presence through their effects on surrounding matter. One way we can see black holes is through X-ray telescopes. When matter is drawn into a black hole, it accelerates and heats up to millions of degrees Celsius, emitting light in the X-ray spectrum. Instruments like the Chandra X-ray Observatory enable us to observe the interaction of black holes with surrounding matter and study them through X-ray radiation. One of the greatest achievements in black hole research is the Event Horizon Telescope, EHT project, a global network of telescopes working together to capture an image of a black hole's event horizon. In 2019, the EHT released the first ever image of a black hole at the center of the galaxy M87. This marked humanity's first visual of a black hole and represents a significant breakthrough in cosmic research. The future of black hole research will involve developing even more sensitive telescopes and technologies, allowing us to observe in greater detail what happens inside and around black holes. Missions such as the James Webb Space Telescope will aid in gathering additional information about black holes through infrared light, potentially unraveling even more of their mysteries. Stephen Hawking proposed the theory of Hawking radiation, which suggests that black holes are not completely black, but can emit radiation and gradually evaporate over time. This theory has sparked significant debates about whether all black holes will eventually die by evaporating over billions of years. Additionally, new theories of quantum gravity are attempting to explain what happens at the microscopic level inside black holes, where current physical laws no longer apply. Some theories, such as string theory and the holographic principle, suggest that our three-dimensional space might be an illusion and that reality might actually exist in a two-dimensional space. An interesting question is the future of black holes. If the theory of Hawking radiation is correct, then over billions or even trillions of years, black holes will gradually evaporate and disappear. This means that eventually our universe might be left without black holes, resulting in an empty void. However, scientists are also exploring the possibility that black holes could serve as gateways to parallel universes, or even as places where new universes might form. Black holes are not only profound mysteries, but also one of the keys to unlocking a deeper understanding of the universe and the fundamental laws of physics. With advancements in technology and new theories in physics, we are increasingly equipped with tools to study and explore black holes. However, the journey to fully unravel the mysteries of black holes is still long, and perhaps in the future, they will raise new questions about the nature of the universe and ourselves.